we go. Yep, they got it. Okay. Hi, good afternoon, everyone. My name is Wilton Moy. It's my honor to be here to give you a talk about low-cost sensors, how to use them, how to plan for a project with them, how to make sure you get good quality data from sensors, because that's a big issue that often happens when using low-cost sensors. So yeah, let's get right into it, and I'll finish by 2:30. So a little bit about me. My name is Wilton again. I think I'm one of the few Americans here who are not from Columbia University and not from the Department of State. So yeah, I'm originally from Miami, Florida, and then I did my undergrad in Florida, and then I moved to California to do my grad school work at Caltech, and I've been an air quality specialist at the Air Quality Sensor Performance Evaluation Center AQ-SPEC program for 5 years, and now I'm the program supervisor. I work at the South Coast Air Quality Management District. This is a regional government agency that manages the air pollution in the Los Angeles area. Yeah, we're basically responsible for improving the air quality from stationary sources. And there are 17 million residents and 4 different counties: Los Angeles County, Orange County, Riverside County, and San Bernardino County, that is under this agency's jurisdiction. Okay, so a few basics about air quality sensors. I think Dr. Rosalani covered a lot of this in yesterday's talk. She did a wonderful job. And I'm going to run through the basics really quickly then, in the interest of time. So sensors, a raw sensor, they're just electronic devices that they sense some kind of physical phenomena, whether that be resistance or current or light. And the major classes of them are electrochemical, EC, metal oxide, or MOX. And then we have a whole bunch of different kinds of optical or light sensors. These can be used for gases or particles. So on the gas side, you can use infrared UV light for sensing certain kinds of gases. And then on the particulate side, you can either sense particles as an ensemble in phelometry, or you can sense them as individual particles as optical particle counters. I'm going to skip a bunch of these because Dr. Alani did a wonderful job talking about this. Okay, so a lot of times when we talk about sensors, we might also be meaning to call them, sensor systems. So as opposed to the raw electronic component, oftentimes lay people mean them in terms of you have the raw sensors plus integrated board and the housing, the power source, and then a means to transmit the data. And here's some illustrations of some pretty popular sensors that some of you may be familiar with. I mean, you could probably see like that one looks like a laser egg, and that one looks like an air beam, and that looks like a purple air, and that looks like an IQ air, that looks like a clarity. And yeah, so I'm going to go into a few differences between sensors and regulatory monitors. So we have a couple examples of low-cost sensors on the left. And just because I show images of particular products, I just have to say this: our agency does not endorse any particular product just because I show it here. But there's a purple air on the left that will measure PM 2.5 and 10. And then on the right-hand side, you've got a BAM that also measures the same pollutants. And then on the lower left, you've got an airly that measures like ozone and nitrogen dioxide. And on the right, you've got a Thermo 49i that measures ozone as well. So these are some examples of the two of sensors and regulatory grade monitors. Sorry, is that a lot of feedback? Okay, I feel like I'm just giving constant feedback. Okay, so some very general differences. Sensors, they're cheap. You can deploy them in a very dense configuration. Oftentimes, as a sensor system, they're easy to use out of the box, but their data quality is often questionable. And for regulatory grade monitors, they're expensive. You need a lot of supporting materials and expertise, but the data quality is generally very defensible and usable for regulatory and policy purposes. Some more granular differences. Sensors, they're probably in the 100 to 5,000 US dollar range, but regulatory grade monitors, they're often exceeding $20,000 USD. Sensors, you might have to pay like a subscription cost, maybe $100 a month, because that's the business model that a lot of the companies are going towards to continually generate revenue. Maintenance costs, they can be significantly more expensive with regulatory grade instruments. And size, noise, and power. Sensors are small, quiet, low power devices. I think we had an example of that during Teddy's hands-on demo yesterday when we were connecting the plan tower to the board, and everyone was like, "Is it on?" And we couldn't hear it, we couldn't feel the fan spinning, but if you stuck a pin in it, then you felt the fan spinning. Longevity. So gas sensors, they typically have a lifetime of about 1 to 2 years, but the particulate matter sensors, they might last about somewhere around the 3 to 5 year mark. Whereas for regulatory grade monitors, the instrument itself is expected to last about over a decade, assuming you're doing the proper maintenance and replacement of parts. But again, we come back to the big hurdle with sensors is their questionable data quality and accuracy, as opposed to the regulatory grade monitors where for policy purposes, we consider them to be the best and they're used as a standard against which sensors are judged. So at least in the United States, we generally view sensors as complementary to regulatory grade monitors. So where you might have a situation where you just have two regulatory grade monitors spaced far apart, we can use sensors to more densely deploy them to fill in the information gaps. And we actually do this as an example in our agency. So prior to about maybe 5 years ago, we had our network of about 30-something regulatory grade air monitoring stations. And you can see that on the map with the gray circles. And then as, like for example, purple air, they became incredibly popular in California and in the United States. And so all the blue dots, those are the purple air monitors just in the Los Angeles area. And so there's been some work in our agency to actually fuse the data, to combine, to supplement our regulatory data with the low-cost sensor data to give a more hyper kind of spatial picture. And what I mean by that is you see how there's like little squares. Those are 5 by 5 kilometer grids in our region that we now provide air quality information on a 5 by 5 kilometer resolution. There we go. Okay. So previously, the information that we had on our website for the members of our jurisdiction, they used to just show air quality information for pretty large regions around each regulatory grade air monitoring site. And then when we combine the purple air data and we have techniques that we use to kind of blend the data, we give different weights to the regulatory data versus the low-cost sensor data. And now we divided our jurisdiction into 5 by 5 kilometers grid cells. And so now on a neighborhood basis, you can zoom into where you live and get a more refined picture of the air quality information. And in some places, low-cost sensors might be the only source of your air quality information. And that's okay. There's ways to kind of address that and get around some of the issues of only having sensors as the source of monitoring. Okay, so there are many data quality hazards that come with sensors. And I've broken them down to 3 kind of general categories. We have data quality hazards that are inherent to the product, those that come with improper setup and operations, and then those that come from maybe not so great practices in analysis and interpretation. So inherent to the product, you're kind of relying on manufacturing quality control, especially if some of the, it kind of comes to the territory, right? If they're low cost, they're inexpensive, you can't really expect the vendor to spend a lot of money on quality control. There are also inappropriate claims from some manufacturers. The brochures will say they can measure this, that, and it's like, 5% off, accuracy of like 95%, but no one's really, challenging them on those claims. It's kind of up to them to self-report that on their manufacturer spec sheet. And as a consumer, you don't really know anything more than what they're telling you on their spec sheet. There's also issues with reliability of data transmission. So sometimes there's issues with the Wi-Fi connection or the cellular connection, and so you have data incompleteness. So maybe you want hourly average data, but you've only got maybe 10 minutes of that data came through on the transmission side. So it wouldn't be accurate to calculate an hourly average from a limited data set like that. And then there are also interferences that are inherent to the operational principle. So for many of our gas sensors, there are cross interferences from other gas species that will affect the reading, from humidity. For particles, the humidity is a big one. Okay, so in the setup and operation, you have to make sure that the way that you install it and the site that you install it is appropriate, mounted at the correct height, that your power situation, your data transmission situation is good. There's often theft, vandalism, and curiosity issues that come with low-cost sensors being deployed out in the general areas. And also, keeping units well-maintained and well-calibrated. That's a really big challenge in terms of staff time and money to keeping your data quality high. And then in the analysis and interpretation side, you have to deal with drift and aging effects. Especially for the gas sensors, they have a very limited lifespan. And so as they age, it becomes more and more difficult to actually adjust the data to account for that. There's also outliers that should be identified. Perhaps the sensors are not calibrated to your local conditions. So when they come straight from the manufacturer, they might be calibrated towards, let's take purple air for example. They're calibrated towards a Beijing kind of atmosphere, which may not be suitable at all for wherever you're actually deploying them. If you do have the fortune to be able to have them calibrated in some way, it's possible that the conditions that they were calibrated at do not actually represent, again, the local conditions that you're actually going to deploy them. There are often unpublished or unstudied performance metrics. Again, oftentimes you have to rely on just the manufacturer's spec sheet, and no one's really checking them on their claims. And then finally, there is the final hurdle, which is the ambiguity in interpretation of the results. So I'm going to walk through a lot of this is going to be about planning, because planning is a huge part of making sure the data quality from your low-cost sensor monitoring project will, in the end, be usable. So planning, I have this nice graphic. It's a 5-part kind of planning cycle: why, what, where, and when, how, and then finally, choose your sensors. I think there's a lot of tendency to go dive straight into just like buying sensors, and then, okay, great, I have sensors, I can go mount them somewhere, get some data, and then you hope and intend that something will come out of it. But if you don't take the time to plan, you might have wasted some valuable money and resources and time, and get information that's not really quite usable for what you originally wanted to do with it. So first, think about why. What is the question that you want to answer, and then what is the goal of your monitoring effort? Do you want to know the air quality of the region, like a more ambient regional kind of picture of the air quality? Are you trying to understand the emissions coming from a particular source? Or is it about more of a personal exposure kind of project? Okay. Next is what? What are the sources of concern? Which pollutants are you interested in? What are some expected concentrations, if you happen to know some possible concentration ranges, so that you can make sure the one you select can measure those concentrations? And finally, which performance metrics are important for the project, and what levels do you need? Because for some projects, you just have to know more on a relative basis. Like if you want to identify certain hotspots of high pollution, it may not have to be accurate, but maybe the sensors have to be precise with each other. Like as a group, they read well together, and if you can have relative kind of differences that you see between the sensors, maybe that's more important. Or if the project is more about educational purposes, maybe accuracy and precision aren't that important, but ease of usability, easiness for a student or kids to be able to grasp and eventually learn the importance and concepts of air pollution. But if your purpose really is having to do with trying to quantify something, make a policy change, or go to the government with some data, then yes, you really do need to make sure that the choice of sensor that you choose displays high accuracy and precision and many other performance metrics.